Okay, so I'm basically going to be going through 9.2, which is about arithmetic sequences and partial sums, and I have tons of examples, more examples than I really have time to go through. So I'm going to just kind of work my way through here, see where you guys are at, and hopefully this will be helpful. So to start off with just some definitions, so an arithmetic sequence is a sequence which has a constant difference between consecutive terms. So you're either adding the same number each term or you're subtracting the same number each term. And it's very similar to a linear equation in that you have a constant that you're adding on basically. The difference is that a linear equation allows all numbers to be plugged in and a sequence is only integers. In general, actually, it's only whole numbers that we plug in. We don't plug in negative numbers into a sequence. But their form is basically the same. They're both in the form of a linear equation. Now, when we say sequence, we're specifically meaning a list of numbers. And when we say the term series, that is basically the sum of a sequence. And then a partial sum is where you only add some of the terms together. And this is used specifically when you have sequences that go on forever. So if you don't have an ending point and you want to find a sum, you'll do a partial sum. So that's just some basic definitions. So we will start with several examples on whether things are arithmetic or not. So the way to determine if they're arithmetic is to find the difference between each term and then see if that difference is the same number for each pair. So that's the definition, following the definition to determine if something is arithmetic. So one way you can look at our first sequence here. We've got 4, 9, 14, 19, 24. So you're basically saying, okay, how do I get from 4 to 9? What is the difference there? So you're adding 5. And then, okay, from 9 to 14, you can do 14 minus 9. But what's going on there? We're adding 5 again. And you look at each pair, and every pair here has a difference of 5. There's 5 between, or you add 5 to get to the next number. So that has a constant difference. Oops. And when we call it a difference, we're basically taking like the second term minus the first term. So 9 minus 4 gives you 5. And if there's a constant difference, which in this case is 5, so we use D for difference, that's equal to 5, that means it's arithmetic. So if you are asked what type of sequence something is, you need to first check whether it's arithmetic using the definition. Is there a constant difference? And then if it's not, then you would maybe check to see if it's geometric. But I'm not going to cover geometric sequences here, but that's a different type. That would be the next thing to check if it's not arithmetic. So same thing, we have our second sequence here. We've got 6.6, 5.9, 5.2, 4.5, 3.8. So decimals, I'm definitely going to use a calculator here because I am terrible at subtracting decimals in my head. So from 6.6 to 5.9, we're subtracting, and that comes out to 0.7. So that's a minus 0.7. So then we will check the next set, 5.9 minus 5.2. We're subtracting another 0.7. Now, just because the first two are negative 0.7 doesn't automatically mean they all are, because sometimes you could have sequences where it looks like they're arithmetic, but it's actually such a small amount of change that you don't realize it's not until it's later on. So you do need to check every single number that you see in the sequence. So this is also subtracting 0.7. And then the last pair here, we're subtracting 0.7. So you have to check every set that you have, and they're all exactly the same. So if they were not exactly the same, like if one of them was negative 0.7 and one was negative 0.69, that's not arithmetic. So arithmetic means they are exactly the same. If they're slightly different, it's not arithmetic. So here we do have a constant difference, and it's a negative because it's decreasing, and so this is another arithmetic sequence. Are there any questions? Okay. So here's one where we're given the formula to get the sequence. We're going to write the first 5 terms and then determine if it's arithmetic. Now, if you have the formula like this, you can tell immediately that this is arithmetic because the sequence, the formula, basically looks linear. So the form is similar to y equals mx plus b, which we know is linear. And so if it's in that form, it's automatically going to be arithmetic because arithmetic sequences and linear equations are basically the same thing, but looking at it at different input values. So we can automatically say that this is arithmetic. So you can do that without even writing the first 5 terms. So you could find the first 5 terms first, find out what that constant difference is, and then figure it out. But you can do it directly by looking at the form and saying, okay, this looks like a linear equation, therefore it is arithmetic. So now when we're asked to find the first 5 terms, we always start counting at 1. So for sequences, we start counting at 1, so that's why we're just looking at whole numbers. So the first term is A1. And so you're just basically plugging 1 in for n and putting it into the formula and determining what your answer is. So we get 8. So A1 is equal to 8. So the first part of the sequence is 8. Now you want to be careful. Just because the form is similar to an equation doesn't mean that, like a linear equation, your y-intercept is sort of like your starting point. The y-intercept, or if we had would be if n was equal to 0, that would be 5. But our first term in the sequence is not 5 because we're not counting from 0, we're counting from 1. So you want to be careful. You can't just automatically look at the equation and say A1 is 5 and the difference is 3, because it's not. A1 is not 5 because we're not starting at 0. So then we can find A2. And you plug in 2 for n, so you got 6 plus 5, so that's 11. And you can see the difference between 8 and 11 is we're adding 3. And that's because that's the number essentially in front of the n. That's sort of giving you what that difference is. So then the third term would be when n is equal to 3. So 9 plus 5 is 14. Again, we added another 3 there. Then we have the fourth term. So 12 plus 5 is 17. And then the fifth term is you plug in 5 for n, and that gives you 20. So our first 5 terms are 8, 11, 14, 17, and 20. And then the pattern would continue. So our difference there is 3. And you can see that because that's 3 times the n. So we're going up by 3 for each n that we're going up by 1. But our starting point is not at 5. It's actually at 8 because we're starting with n equals 1. Any questions? Okay, so next example here. Again, we're going to write the first 5 terms of the sequence and determine if it's arithmetic. So we have n equals 1 plus n minus 1 times n. So this is not immediately in the form of like mx plus b. And one thing that I notice here is that if I was to distribute the n minus 1 times n, if we were to multiply that out, I would get n squared minus n. And that definitely does not look linear. So it has like an exponent in there. If you try to simplify it and you don't get something that looks linear, then it's not arithmetic. So you can look at the equation again and determine, okay, I'm going to end up with something squared or something like that, and it's automatically not going to be an arithmetic sequence. And you can verify this by finding the first 5 terms, and you'll see that you're not increasing by the same amount each time. So our first 5 terms, if we have a1, we have 1 plus, and then n is 1, so that's 1 minus 1 times 1. So 1 minus 1 is 0. 0 times 1 is 0, so we're just left with 1. Our starting point here is 1. Second term, we have 1 plus, then we have 2 minus 1 times 2. So 2 minus 1 is 1, times 2 is 2, plus 1, we get 3. So far the difference here is plus 2. Third term, 1 plus 3 minus 1 times 3. So 3 minus 1 is 2, 2 times 3 is 6, 6 plus 1 is 7. Now notice we added 4, 3 to 7. So we don't have a constant difference there, because if it was a constant, if it was the same thing as plus 2, we would have been at 5, but we're higher than that. So this is not arithmetic, and we're basically proving that to ourselves or verifying that by plugging in and finding the first 5 terms. So the fourth term is 1 plus 4 minus 1 times 4. So 4 minus 1 is 3. 3 times 4 is 12. Plus 1 is 13. And so now between those two, we added 6. So we're adding more each time. So again, not arithmetic. And then the last term they want us to find, the first 5 terms. So term 5 is 1 plus 5 minus 1 times 5. So 5 minus 1 is 4. 4 times 5 is 20. Plus 1, we get 21. And that is a difference of 8 there. So we're definitely not increasing by the same amount each time, so it's not arithmetic. And our first 5 terms are 1, 3, 7, 13, 21. And then you can see the pattern that the next one we add 10, you know, you can see what your pattern would be, and you'd see that the next one would be 31, and you can follow that pattern. Are there any questions? Okay. So here's another one. Is this arithmetic? So looking at the equation, I want you guys to tell me, do you think this is going to be arithmetic or not? Like if you had to make a guess. Okay, Dotton, you say you don't think it is. We can check. And Elliot, you're going to say no because the n has an exponent. So you guys are in agreement, basically. You're thinking that no, it doesn't look arithmetic. And let's check, see if this is right by finding our first terms. So n is equal to 1, so we have 1 minus -1 to the first power. So -1 to the first power is -1. So we 1 minus -1, which is 1 plus 1. So we end up with 2. So let's look at our second term. 2 minus -1 squared. So -1 squared is +1. 2 minus 1 is 1. Now let's look at our third term. So we have n, which is 3 minus -1 to the third power. So -1 to the third is going to be -1. 3 minus -1. Now we're jumping up to 4. So you guys are correct. This is not arithmetic because we went down and then we went back up. And the key is if you've got something with that exponent where the variable is in the exponent, it's not going to be arithmetic. Because again, it doesn't look linear. And this specific, anything where you have a -1 to the end, that means you're going to be alternating up and down. So indicates, let me spell a little better, that you're going to go up and you're going to go down, because -1 to an exponent just basically oscillates between a +1 and -1, +1, -1. And so you're going up, down, up, down. And if you're going up and down, you're not going to be increasing by the same amount each time or decreasing by the same amount each time. So that automatically means, well, this can't possibly be arithmetic. And we'll finish out finding our 5 terms. So that would be 3 minus -1. And that is going to be 6. So it's like you're going down 1, up 3, down 1, up 3. So you're going, in this case, you're going down, up, down, up, down, up. And the amount we're going down is the same. The amount we're going up is the same, but all together they're not constant. So this one here, we have a to the n equals 2 to the n times n. Same thinking. We've got an exponent with a variable. So that automatically is going to tell us that this is not arithmetic. Not only that, but we're also multiplying by n. Now, if this was just 2n, if there was no exponent in the variable or variable in the exponent, it would be arithmetic if we just had 2n, because you're just multiplying by 2 each time. You know, you go 2, 4, 6, 8, you're adding to it each time. But because we have this exponent here, that automatically means that this is not arithmetic. So first 5 terms, you'd have 2 to the first times 1, so that's just 2. Then you have 2 squared times 2, which basically ends up being 2 to the third power. So we got 8. Then third term, 2 cubed times 3. So 8 times 3 is 24. You can see very clearly we're increasing much faster. We're not increasing by a constant amount. Fourth term, 2 to the 4 times 4. So 2 to the 4 is 16 times 4, I think is 64. Yes. And then fifth term, 2 to the 5th times 5. So that's 32 times 5. We get 160. So very clearly not arithmetic. And that's because of that exponent. That exponent means we're going to be increasing faster each time. So next, you know, if you're given a sequence and you need to write an equation for a sequence, you first have to determine what type of sequence it is. So the first step would be, is this an arithmetic sequence? And then if it is, how do I write a formula for that to help me determine the formula so that I can figure out each term or figuring out the sum? So we'll start with the terms. So we do have a formula to find a specific term of an arithmetic sequence. So it's not finding the sum, it's just finding a specific number in a certain spot in the sequence. So first you have to determine its arithmetic, and then we have this formula, an equals a1 plus n minus 1 times d. So you can see that's very similar to mx plus b. You have some number, and then you're adding on another number times your difference, you know, and your n is changing. We could rewrite this if we wanted to. So if I wanted to, I can write this as a1 plus n times d minus d, you know, if you distributed through. And you could have an alternative form that looks a little bit more linear if n was your x, so to speak, your input, where you have a1 minus d plus n times d. So either form of these is fine. The form that we have on top with the n minus 1 is typically the form that we write these in. But this will give you specific number in a location. It doesn't give you the sum. And then there's a recursive version of the formula, which is a to the n plus 1 is equal to an plus d. Now, in computer programming, you often take advantage of recursion, especially if you're doing things where you're adding 1 to each term, or you need to add 2 or something like that. I mean, you basically will do that if you're in a loop, and you'll do that recursively. And so the form here for an arithmetic sequence is basically what you would see if you were to write a loop where you're increasing by 1 every time or increasing by 2 each time. That would be your d, and then you would just take that previous variable, add d to it. That gives your new value. So sequences and recognizing sequences, that actually connects to computer programming, especially with the recursive part and trying to come up with these formulas. So we're just going to go through a whole bunch of these and come up with a formula. And first, you always have to check first to see if it's, you know, arithmetic before you actually do the formula. But these are all going to be arithmetic, so we're not going to check that. But we're going to find a formula for a to the n, or an, given the sequence, and we're giving different qualifications here. So the formula that we generally use is A1 plus n minus 1 times D. So that's going to be the formula that I'm going to use for these. I recommend just writing it down. And if you're given A1 and you're given D, all you have to do is plug in the numbers, and you don't even need to do any like simplifying or anything like that. So A1 is 0, n is our variable, and so we have n minus 1 times negative 2/3. Some people do like to simplify this, so I could rewrite this as negative 2/3 n plus 2/3 if I wanted to distribute through the parentheses and make it look a bit more linear. So you can do that if you want. But as long as you're given the first term and the difference, it's really easy to come up with a formula. It's just plugging it in. That's all you're doing. And then once you have the formula, you can find any term by plugging in a number for n. So if I wanted the 1,000th term, I could just plug in 1,000 for n, and then that will give me that point. Having the formula is very beneficial if you have to find terms very far down the sequence. You're not going to want to have to sit there and add it up each time, because that's going to be just like a lot of work. So here's where it gets a little tougher, is when you're given the sequence, but you're not given like the difference and things like that. So that's where you have to find what those values are. So the first number is always going to be A1. So we can determine the first term of the sequence here is 4. From there, you need to find the difference. And in regards to showing your work, even if it's something you can do in your head, you should write down what the difference is. So you should at least making sure you write down D equals and then whatever it is. Now in this case, I can't do this in my head because it's got fractions, and I'm not that great with fractions. So I would actually write out, well, how do I find that difference? So we would take 3/2 minus 4, and then that would give you your difference. And you know, I could be lazy and use my calculator, which can work with fractions, and just have it do this for me. I would get -5/2. So that is the difference. At the bare minimum, you need to at least write down D equals and then what it equals. You want to write down A1 equals, you know, at least write down what your values are for your sequence. Next step is to plug it into that formula that we have. AN equals A1 plus n minus 1 times D. It's always good practice to write down the formula before you start plugging numbers in. It helps you remember the formula, and then it helps communicate to others what you're doing, where your equation came from. It came from, okay, here's our formula, and now I'm going to plug in those numbers. So it's always good practice to write that down. And I'm only doing it in a different color just to show that that's the formula. You don't have to color code or anything like that. But then we have AN equals 4 plus n minus 1 times -5/2. And I need to put the -5/2 in parentheses there so it doesn't look like that I'm subtracting it, but I'm multiplying. And if you wanted to, you can rewrite it so that's in front of the n minus 1, just so it looks a little easier for our eyes. If you've got a fraction here, I wouldn't even say that there's no reason to try to simplify it. You could just leave it in that form, because we can still see that it's an arithmetic sequence. It's still in the right form. There's no reason to try to simplify it further unless you're asked to. Are there any questions? Okay, now here we want to find a formula for an given the arithmetic sequence with a1 equals 5 and a1 equals, or a4 equals 15. So we're given a1, but we're not given the difference. So we need to kind of figure out, well, what is that difference? So there's two ways to do this. And the first is by basically going off of our formula. So if we plug in what we know in the formula, and we can plug in A4, which is 15, A1 is 5, N is 4, you can plug in that known information, and then you get an equation that you can solve for D. So you can find that difference. So if we do that, we get 15 equals 5 plus 3D. You'd subtract 5 from both sides to give you 10 equals 3D. And then divide both sides by 3 to get your difference, and that's 10 over 3. Now, the alternative to doing it this way is to go back to the fact that an arithmetic sequence is very similar to a linear equation. And so you can use the slope formula, essentially, of a linear equation to find the distance, or the difference, basically. So if you wanted to, you could take the output values of sequence values 10 minus 5 and divide it by the ends, 4 minus 1, and you get the same value. And that's because there is essentially a relationship between an arithmetic sequence and a linear equation, that they both have that constant difference, and the constant difference in a linear equation is the slope. So the formula is essentially the same. So you can do those either way, and this only works with an arithmetic sequence because of the fact that it is related to the linear equation. But once you find D, and you already have A1, so then you can write your equation. AN equals 5 plus N minus 1 times 10 thirds. So you could just leave it like that if you want. So here's something that's a little similar. Again, we're going to find A to N, but we have the third term, which is 94, and the sixth term, which is 103. So we're not given the first term, but we know two other terms. So just like the previous example, there are two ways that we can do this. And the first is by using our formula for the arithmetic sequence. AN equals A1 plus N minus 1 times D. So we don't know A1, we don't know D, but we can use these two values they give us to get a system of equations. Where if I plug in A3, it's 94 equals A1 plus 3 minus 1 times D. And if I plug in 103 for A6, I get another equation where I have 6 minus 1 times D. And now we have a system of equations because we have two equations. Oops, that should say A1. Two equations, two variables. And you could solve this. I would use this. I would probably solve this using the elimination method, because if I just change the signs in one of the equations, I can make A1 cancel out pretty easily and then solve for D. So if we went ahead and do that, so first equation, 3 minus 1 is 2D. Let's say I switched all of my signs in the second equation to make them negative. So 6 minus 1 is 5, so then that would give me a minus 5D. So 94 minus 103 is -9. A1 minus A1 is 0. 2 minus 5 is -3. And then divide both sides by -3. And we get the difference is 3. So once you find D, then you can go and plug it in like we did on the previous example. We can now find what A1 is. So I can plug it into one of the equations. So let's say I plug it in to the first equation here. So I can plug in 3 for D. So we had 94 equals A1 plus 6, and then subtract 6 from 94. And we get A1 is equal to 88. And then that would give you enough so that you have your formula. AN equals 88 plus N minus 1 times 3. Or I like to put that, the D in front, 3 times N minus 1. So that's one way that you can solve this, is you create a system of equations, solve, find D, and then you can plug it in, and then you can get A1. Or if we wanted to, you can find A1, plug it in to get D, either way. The alternate way is to, again, use the slope formula to find D, like we did in the previous example, where you do 103 minus 94 over 6 minus 3. That gives you 9 over 3, and then that gives you 3. Now you still have to plug D in to solve for A1, so you'd still have to go to this other step here. But it is less work. I mean, it's a lot less work than actually solving a system, and it gives you the same answer. But this only works because it's an arithmetic sequence. This would not work for like a geometric sequence. Are there any questions? Okay. Okay, so now I'm going to throw in some recursive sequences just to give you some practice with those. So we want to write the first 5 terms given the arithmetic sequence with A1 equal 200 and AN plus 1 equals AN minus 10. So first 5 terms. When I do something recursive, I find it easier for me to write down what n is, just so I don't get confused. I don't need to do this when I don't have a recursive sequence, but when I have something recursive, because you've got n and n plus 1, I just find it a lot easier to kind of write down what n is so I can kind of keep myself organized. So we already know what A1 is because they've given us that. That's 200. So here we have this recursive part. So this is n plus 1. So if n is 1, 1 plus 1, that would give us a 2. And that is equal to an, which is a1 minus 10. So a1 is 200. So we're subtracting 10 and we get 190. And so that number is now basically our input for the next line. So the way that I'm doing it is I'm not doing the work at n equals 2 because our recursive, we have to use the work from the previous line. So my work is going along with the first n, and then that gives me my second term. So again, an plus 1, so if n is 2, this is going to give me a 3. and then it's AN, so I'm in the line with n equals 2, so that's A2 minus 10. So that's 190 minus 10, we get 180. And that's giving me my next value. Now you can see the pattern. The nice thing about recursive is that you can see you're just subtracting 10 each time. And that just comes from the formula there. This is a simpler pattern, so it's not too complicated, but you're just subtracting 10. So you can follow that pattern, and then you can get your next 5 terms, or the next terms, just by subtracting 10. But I find by lining it up this way, sometimes if you don't do it this way, you may find yourself skipping a number. Like you might say, okay, I have A1, and then start with n equals 2, and that will give you A3, and then you've skipped a number, and then that can throw you off. So that's why when I do stuff recursively, I line it up the way that I have. And so it's like I'm taking my current input, and then that gives me the next number, and then I start anew, and that's my next input. If you've done programming, this will probably make more sense with you, especially if you're doing loops where you have an input, you do some math, and then that gives you your output, and then that's what you have in the next line. So this is sort of how it's kind of very similar to doing your loops to get to the next point. So I'm going to do the same thing here. So we've got the first 5 terms, given the arithmetic sequence with A3 equals 0.5, and then AN plus 1 equals AN plus 0.75. So the way that the arithmetic sequence is written recursively, it means we're adding 0.75 each time. So that's nice, except that they don't give us A1. So I'm going to just make my rows again. So we're given A3, which is 0.5. Now, because the recursive is telling us that we're adding 0.75 each time, the way that it's written, it's a previous term plus 0.75. All I have to do is add 0.75 to get to my next terms. So getting to term 4 and term 5 is pretty nice because that formula, like there's less thinking to do when it's in recursive form, because it's literally just telling you, okay, you add 0.75 each time, and that gets you to the next one. So because we have started at A3, we need to go backwards. So you do the opposite. You subtract 0.75. If we added it to go forward, to go backwards, we're going to subtract. So A2, 0.75, or 0.5 minus 0.75 is negative 0.25. And then we subtract 0.75 again, and we get negative 1. Now, you could use your formula to actually solve for each of these. So if I have A3 and say that's n plus 1, A3, then this would be A2 plus 0.75. So you can solve by putting in the value for A3, 0.5, and then you can see you subtract 0.75, that gives you A2. So we can even take this arithmetic sequence when it's written recursively and solve for the previous term, AN, and that would be AN plus 1 minus 0.75. Sometimes when you have things that are recursive, instead of referring to these as like AN and AN plus 1, sometimes it's just easier to put what it means. You know, the next term, and then say like maybe current term, to kind of put it in words to help you Let me write current better. Just so that it makes more sense in context what you're finding. Or, you know, if we're solving backwards, then the current term, we can say this is the current term, which means this is the previous term. But if the an plus 1 and the an is kind of confusing, you can use words there instead. But I'm going to put these back into what we did. An plus 1 minus 0.75. At least when I'm doing computer programs and I have to do things like this, I will use terms like current and next just to help me when I'm programming, so I know exactly what I'm looking at here. I won't call my variable like an and an2 or, you know, something like that. Are there any questions? Okay. So next are going to be finding sums of arithmetic sequences. So we found terms, now we're going to find sums. So we've got a formula to find the sum. And so we use S to indicate sum, A is for term. So you want to make sure that you're using the right letters so that you are, you know, indicating the correct thing. If you use the letter A when you're supposed to use S or vice versa, then what you've written is incorrect. And it can kind of get confusing. So S is for sum. And then when we say Sn, that's how many terms we're adding up. So if it's S5, we're adding the first 5 terms. And so the formula is basically the number of terms divided by 2, and then A1 plus AN. Essentially, if you think about it, we can rewrite this, and you can think of it as taking the first term and the last term and averaging them and then multiplying it by the number of terms. I mean, that's what this formula essentially means, is that you're taking the first and the last term in your sequence, average them, and then multiply by the number of terms. I don't know why they don't write it that way, because that's essentially what you're doing, but instead they write it this other way. Now you could get creative if you want, like let's say you don't know what the last term is. We know what the formula is for that term for AN. So you can plug that in for AN. So I've basically, this is our formula for AN that I've just plugged in. And then all you have to do is some algebra, manipulate it, and you get a new formula for a sum of a sequence where all you need to know is the first term, the difference, and then how many terms you're adding up. So the book doesn't give you this formula. The book only gives you the first formula. But I often see students looking online for formulas and using the second formula, so I thought I'd at least show you where that comes from. It's just from some algebraic manipulation where you're just plugging things in. And so if, say you don't know what that last term is, but you know the first term, you can still find the sum, which kind of is really nice. It saves you some work. So let's find some sums. So we're going to find the sum of the finite arithmetic sequence. And so we need to count how many terms we have. 1, 2, 3, 4, 5, 6. So n is going to be 6. So we're going to find S6, the sum of the first 6 terms. So because we know the first term and the last term, I would use the first form of the sum formula that we have. And again, I'm going to write that down. So Sn is n over 2 times A1 plus AN. So when we're using that formula, all you need is the first term and the last term here if you have a sequence. And then I need to make sure that I label this as S6. We're adding 6 terms together. And this is 6 over 2. And A1 is -5. And AN, or A6, is 5. So -5 plus 5 is 0. We're just going to get a sum of 0 here. And it makes sense if you're looking at the sequence. We've got the negative numbers and then the positive, everything cancels up. So you could totally just, add this up by hand. But when you have a sequence that's much longer, you're not going to want to do that. So unlike the homework, even if you have a sequence you can add by hand, use the formula, because the whole point of the formula is the whole thing is to demonstrate that you can use these formulas so that if you're asked to add the first 20, you can get an answer faster than literally writing out the first 20 terms and then plugging them into your calculator. So this is a problem easy enough to do by hand, but if we use the formula, that shows how you can use the formula, and it works, with much larger lists of numbers. So I'm kind of running out of time here, so I'm going to try to speed through here. So here's an example where you would not want to do it by hand. Find the sum of integers from -100 to 30. You're not going to want to add all those up together. The formula is very helpful. Now, in order to, you need to kind of know how many numbers you have. We need to know what n is. So it might help to just kind of write out a few terms. And to just kind of write the pattern here. So this is our list of numbers from -100 to 30. And we need to know how many numbers are there in that list, because we need to know n. That's what required for our formula. Well, 1 to 30 is 30 numbers. We have one number with 0. And from -1 to -100, there are 100 numbers there. So if you add all of these together, we have 131 numbers that we're adding together. So it's really important when 0 is included that you have to make sure you count that. Otherwise, you'll be off by 1. Because when we start counting, counting doesn't start at 0, counting starts at 1. So you have to manually make sure you add that one in. So we've got 131 numbers here. And we know A1 and A131. Our first number is -100. The last number here that we're adding is 30. So our sum formula, again, I'm going to just write down the formula. N over 2, A1 plus AN. So we're finding S131 equals 131 over 2. And then A1 is -100. And then A131 is 30. So I'm going to just put this in my calculator. And I got -4,585. So you certainly would not want to add that up all on your own. But that would be what these sum up to. Any questions? Okay. Here we want to find the 25th partial sum of the arithmetic sequence 75, 70, 65, 60, we don't know what the 25th is. We know what the first one is, which is 75. Let me write that a little better. But we don't know the 25th. So this is where I would use that alternate form of the equation that I basically solve for. I would use the one in the bottom so that you don't have to go and find an. We can just use this one in the bottom. So that's Sn. And I do not have this one memorized. So I'm going to have to keep going back and forth. A1n A1 times n plus n times n minus 1 over 2 times d. So it's kind of a messier looking formula, but it has everything that we need. So we do have to find d here. So that's 70 minus 75. So d is -5. And we know that A1 is 75. And if we're finding the 25th partial sum, n is equal to 25. So we have S25 equals A1, which is 75, times n, which is 25, plus 25 times 25 minus 1 all over 2 times -5. So it's going to be, I mean, you've got some math here to do. We're going to get some pretty large numbers. 1875. 25 times 24 divided by 2. This is 300 times -5. You add this all together and we get 375. So it's not too much work. It's definitely a lot better than, or a lot easier than trying to first get a formula for Sn or An, then plugging in 25 to find what An is, and then you can then use this formula or the regular sum formula. You can plug it in. And I actually might end up being about the same amount of work. I'm not, we could compare it. But this is one way to do it, because you have A1, you can figure out D, and then all you need to do is plug in numbers. One thing that I would do if you're doing this on an assignment, though, is, again, make sure you're writing down the formula that I have in blue. Make sure you're showing your work, writing down what A1 is, writing what D is, writing what N is, and then plugging in the numbers, and then showing your work to get to your final answer. So you don't want to skip things. You want to make sure that you label each number that you're using. Are any questions? Okay, so I have way more examples, but like I thought I was going to have enough time to go through all of it. This is a long enough video as it is, but hopefully this has been very helpful. This will definitely help you on the assignment. Just make sure before you do anything on the assignment, you determine whether it's arithmetic or geometric, because that will determine what methods you use. And I do have a video on geometric sequences as well, but the first step is to determine this type of sequence so that you know which formulas you need to use.